Hello and welcome everyone to this 26th, if I'm not mistaken, episode of Iron Beetle, a Twitch and a YouTube show where we try to understand how Beetle, this new exciting database for financial accounting, works underneath. Hello, Brian, if that's you. Nice to see some people in chat. As usual, you can ask your questions in Twitch chat. That's very helpful to make the episodes more lively and to actually explain what is unclear rather than to explain what I wanted to explain. Except that I'm not logged in Twitch today, so I won't be able to type answers here. So, okay, let's get started. As a reminder, the grand arc is that Beetle is a distributed database, and it contains roughly three big parts. One part is the state machine for double entry bookkeeping, the financial accounting per se. Then there is consensus. Consensus is responsible for coordinating processing of financial transactions across 6 replicas of a cluster in such a way to ensure that every replica processes exactly the same set of transactions in exactly same order. Finally, there is a third part, the storage. This is what we are looking at for the past few episodes. The storage is responsible for durably persisting the data on disk and for storing this data after this crash. So this is actually two different but crucial roles that the storage plays. First of all, using storage allows us to store more data than just fits in RAM. And second of all, storage allows us to crash and restart and not lose data. It's interesting that you could actually potentially achieve high availability even without storage. So, for example, the original ViewStamp replication revisited paper describes a consensus algorithm which executes without durable storage and which guarantees availability as long as you have F+1 replicas online at any given point in time. So kind of like, your consensus actually levitates on top of disk. But that's, of course, doesn't work if all your replicas shut down simultaneously, which might be the case. So that's why we use storage. Okay, so how exactly are we storing data? We are storing data in an LSM tree. So LSM tree, and here we open the source code. LSM tree is a sorted array of values. So very simple data structure, probably the first data structure you've learned in your computer science classes, like just sorted array, except that it is stored on disk. So how the data in an LSM tree is organized? We start with schema.zig, where we have data blocks and index blocks. So data block is just a sorted array of values. Can I zoom? Yes, I think I should be able to zoom a little bit. Zoom in, zoom in. Okay, so if I zoom in any more, then I won't be able to see enough of text on the screen, so that's probably the largest font we can afford here. Okay, so data block. Data block is just a sorted array of values, like the simplest possible thing you could imagine. Then, if you have a bunch of data blocks, you could arrange them together. A bunch of data blocks such that blocks are disjoint. So every block contains a sorted set of values, and the ranges of any two blocks are disjoint. Then you can sort the blocks themselves and put the addresses of these blocks into a different block called an index block. And what you have is a table. So a table is two-level data structure. You have index block, you have data blocks. When you want to find a value for a particular key in a table, you first binary search the index block because, well, the index block, in addition to addresses of the data blocks, it also includes the minimum and maximum key of each data block. So you can binary search the index block. And then you binary search the data block within that index block. Now, that's a table. How tables are arranged. So this is crucial. The set of all the tables is kept in memory. So at any given point in time, somewhere in random access memory of a targetable process, there is a data structure which stores every single table together with a minimum and maximum key, or, well, I think it's only maximum key, together with a maximum key for the entire table. So if you want to look up data in this data structure, well, you first find the correct table in your in-memory data structure, and then you go to disk and drill down this table, reading the index block from disk, reading the data block from disk. Oops. The specific way these tables are stored in memory is as a series of so-called manifest level. So we have manifest level, and manifest level to a table is what an index block is to a data block. So a level contains a set of tables, and the tables are also disjoint. So you could binary search the level to find the table, then binary search the index block of the table to find the data block, and then binary search the data block to find the value we're looking for. So that's a single level. Now, there are multiple levels, and this level structure is where we change the rhythm and where we do something differently. While before we always had like disjoint ranges, it might be true that two different levels actually contain intersecting ranges of keys. It might even be the case that a particular key is present in several levels. And in this situation, what we do is that we say that earlier levels just shadow any later level. So if you find the key in level 0, then you don't go to level 1. You said, okay, I found the key in level 0, and that's my answer. And if you don't find, and if you didn't find the key in level 0, only then you go to level 1 and all the way to the level 7, the latest level. If you didn't find anything in the 7th level, then you say confidently, hey, this key is not part of my tree. The reason why we need this level structure is that it allows us to mutate data. So because earlier levels shadow new levels, the way you can model mutation in this data structure is that you can just take a bunch of changes, arrange them in a new level, and slap this level on top of the structure. And that way you kind of like incorporated changes to your data structure. Specifically, the way this changing works is through manifest log. So we have manifest, which is the set of all tables in memory. We have manifest level, which is a set of tables on a single level. And then we have manifest log. So manifest log is a sequence of operations which, when applied to an empty manifest, give you the actual manifest that you have. And operations are really simple. So operation is just, hey, this is a table. So table is identified by the address of its index block. This table was either inserted, removed, or moved from layer to layer, and well, this table was inserted in this particular level. So that's it. Very simple data structure. Okay, so these events are stored in, and now we go back to schema.zig, are stored in manifest node blocks. So each manifest node block stores a bunch of these atomic events for the manifest, and then a pointer to the next manifest node block. So the way you reconstruct manifest is that you take the first manifest node, apply events from it, and then follow the link to the second manifest node, etc., 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 until you hit the end of a linked list. And in the end, you get your in-memory data structure, which represents a set of whole tables, the entire set of tables in your database, which in turn allows you to do operations with this data. So today, we are finally approaching the end of this, hey, how the data is like actually organized, like how everything is holding up together. And today we learn how we get this first pointer to this manifest node, because this is the magic. We only need one pointer, and when I say pointer, I mean a pointer to a block on disk, which is actually two fields: the address on disk and the checksum we expect this data to have. So this is the magic. The entire state of the disk of the target database is contained in just two numbers: a U64 address of the first manifest node and a U256 checksum of this manifest node. So if you know this address, if you know this checksum, you go and read your first manifest node and you reconstruct part of your manifest. And then in this manifest node, there is, how is it called, next or something, previous. Yeah, it is called previous. There is a previous block, which is just a field in the header of a block. So we go to the metadata, and then we go to, and the metadata contains this like previous checksum, previous address. And to get metadata, we basically just get the header from block, and we get the header from block by just casting the prefix of a block to the header, and then we cast something else to the metadata. Yeah, okay, we cast part of this header to the metadata. Okay, so this all seems pretty reasonable. The question is like, how do we get to this first block? Where was like the start of this cat? Okay, so and that's the trick. So this is going to be one place where we are going to violate the core invariant of target. So the core invariant of target is that whenever you are reading a piece of data from disk, you do it using both the address of the thing on disk and the checksum. You always want to have checksum be communicated to you out of band from the actual data on disk. And the reason for that is that one failure mode for disks is misdirected reads or writes. So if you store the checksum with the data itself, it might be that if you store the checksum in data itself, it might be the case that you ask your disk to write this data somewhere, and the disk writes this data exactly as it should be, byte for byte, identical, but at the wrong offset. And then sometime later, you read data from that offset, and well, you get a data with a consistent checksum, but that's wrong data. That's why you need to have checksum from something else. And so far, the story is that as long as we have a checksum for a block, this checksum comes from a different block. So for a manifest node, the checksum is coming from the previous manifest node. For the index block, the checksum comes from the corresponding manifest node, which added this table. For a data block, the checksum comes from the index node. The question, how strong is the checksum? What's the algorithm? So the checksum is cryptographic. We assume that collisions do not happen, and we give 128, well, it's actually curious. We give 128 bits for a checksum, but actually on disk we reserve the whole 256 bits. So with accounting for both the paradox and assuming that there is no collision purely by random, that should be enough for the size of data file we intend to support. Now, what is the checksum? So traditionally, for this kind of applications, people use Blake-free checksum, because Blake-3 is really, really fast. And Blake-3 is really, really fast, even if it is implemented in software. For us, at one point, we actually measured and figured out that, hey, Blake-3 isn't actually as fast as it should be, which was a combination of two things. First is that just the implementation of Blake-3 in the external library at that point was slower than the one from Rust. So there were like some opportunities for optimizations, but even then, kind of like Blake-3 actually isn't the fastest possible checksum you could use. And the reason for that is kind of like the benefit of Blake-3 is that it runs quickly in software. And well, like to clarify, right now I'm talking about something I have absolutely zero idea about. So I'm like not a cryptographer. I have very vague understanding about checksums and whatnot. So like probably I'm telling you lies, but at least this is funny. Okay, so yeah, the strength and the weakness of a Blake checksum is that it runs pretty fast using normal operations. And turns out that most modern CPUs actually have some pretty decent hardware accelerated cryptography primitives. In particular, primitives for AES, Advanced Encryption Standard. And it turns out that what you could actually do is that you could take this idea on which the Blake-3 is built on top of, which allows it to run really fast because it uses things internally, because it like has a lot of data parallelism for computer checksums. And you could replace the operations like the kernel that Blake-3 uses with these advanced encryption standard primitives, and what you get is a checksum which is pretty slow if you run it in software, but if you actually run it in hardware, it is super fast. And yeah, that's what it is here. This is like IEGIS checksum. It is. I think this is kind of like an upcoming new thing. Like there is a paper and whatever, but it's not like widely deployed. But well, that's what we use here. And again, for us, like this is a non-Byzantine situation, so we kind of like don't necessarily care about someone trying to deliberately attack the checksum or something like that. Okay, And just to show kind of like what I'm talking about, these IS instructions. Absorb, okay, AS block, you see how does it actually work. Soft, so soft is probably soft is probably software implementation. It's not what we're actually using. It's probably this thing. Okay, a single AS block, and okay, yeah. So this is why this is fast. So two reasons. One is that the overall construction, which my understanding is the same between Blake 3 and this IAGIS thing, where we kind of like try to hash things in parallel so that everything is like super fast and vectorized. And then, this is like secret sauce, is that for the actual kernel operation, we use this specific assembly instruction for Intel. This does mean that Terabitl needs a fairly recent CPU to run, and if you run it on like CPU from like 2009, you get some obscure crash which says illegal instructions, whatever. But well, we kind of like trying to made the roads wide not for today's but for tomorrow. So hopefully, like by the time Terabitl is widely deployed, these kinds of instructions will be commonplace. And well, kind of like it's not that we are super dependent on a particular checksum. So you could just change this checksum to be something else, and that would be pretty easy to do. Okay, well, model of course that hey, your checksum, like your data file, of course uses like existing checksum. So like migrating existing data file to a new checksum is going to be hugely complicated, but changing new data files to different checksum would be pretty easy. Okay, yeah. So hopefully that answers the question about how strong is the checksum used by Terabitl, with the very definite answer that I don't know, but well, my understanding is that it's like pretty much cryptographically a secure checksum. Okay, so let's come back to that mystery that when we read a data block from disk, okay, when we read the data block from disk, we add another incoming question for chat. Can you run Terabitl on ARM or RISC-V? Well, I think we do. Well, just like let's go and check if we have builds for ARM. So PowerShell Linux, okay, it's not here. I think we do have ARM builds. Okay, yeah. We built universal images for macOS. That means that for macOS we actually include both ARM and x86 version for build. So yeah, you totally can build Terabitl for ARM. I don't think we ever build it for X5, but well, it should be possible. Of course, like if your CPU doesn't have this hardware accelerated advanced encryption standard thing, then it's going to run prohibitively slow. It's not. I mean, like it's going to be like okay for like normal software, but like for Terabitl performance target, it's going to be prohibitively slow. But even for ARM, again, you do have this hardware acceleration. So again, we looked at there's like again, I'm not sure if Zigbee Server shows me all the implementations, but we have at least one for x86 and one for ARM. So perhaps there is like more hardware implementations for different architectures. is it possible to build Rust for different platforms using Zeek? That's actually possible. You could use Zeek as a dropped-in compiler and linker, and I think actually this is like one of like interesting ways to cross-compile Rust when you just say, okay, so like my I don't know, I want to build some piece of Rust software, and that piece of software depends on some C code, like for example on libc, so I need to cross-compile libc. So I'm going to use Zeek CC as my cross-compiler to cross-compile the C bits, and to use the Zeek linker as Zeek also as a linker for cross-linking, and that presumably works, but well, I kind of like didn't try that. Okay, so the solutions, but okay, let's get to the mystery. I'm curious. Like this is such a big mystery. Like how, like if we always get this checksum from elsewhere, how do we get like the first checksum? And you are not interested in like learning about this. You ask me interesting questions about checksums and whatnot. Okay, so yeah, the rule. If you read a block from disk, you need to get a checksum from a different block of disk. The question: how do we get like the first ever checksum? So imagine you are a replica, you just started, you have no idea what is your state, but you have like your data file. So you read a bit of data from the data file, but you don't have a checksum because well you've just started, and kind of like well you might read something from this data file and you might use some internal checksum, but well what happens if the checksum matches due to misdirected read? What if what if a checksum lies to you? And here we come to this idea of a superblock. So superblock here. Okay, so this is like really like the core thing. Again, I say that this is the core thing in every single episode, and well, this is one of the core things. Superblock. It's really super. It's not an overstatement. So, what's the idea behind this superblock? This is actually pretty simple. So, superblock is the root of a state, and in particular, superblock is going to contain the pointer to that first manifest node, which would allow us to reconstruct the entire LSM tree in memory. And this is stored in manifest newest. So you see, actually, well. Okay, this is going to be slightly confusing, but bear with me. Okay, so we have checkpoint state. Within checkpoint state, we have this manifest newest address. The checkpoint state itself is stored itself is stored inside the SR state, and the SR state is stored in the superblock header, and I think as of now actually superblock only contains the header, so it's slightly a misnomer. Like there is there's like superblock header is like basically superblock. Before we had like superblock trailer and superblock header, but we removed the trailers, or I'll move them to a grid, but that's a different story. So okay, so this is like superblock header. This is the thing which contains this SR state, which contains checkpoint state, which contains pointer to the first manifest node, which contains pointers to all the other manifest nodes, which together contains pointers to all the tables in Tragabitol. And it has a checksum. And unlike every single other checksum in the Tragabitol, this checksum like protects the data itself. So here, this again, like as usual, this superblock header is external struct, so we again are going to just read this from disk and then just like cast bytes to this superblock. But yeah, this checksum covers the superblock, and this is kind of like exactly what I said we should never ever do, because if you read something from disk and cast that to a superblock header and check the checksum, and the checksum is correct, you actually don't have a guarantee that this is a valid, that this is that header that you wanted to get, because it might have been a misdirected write. So we do a very stupid trick here to fix this. We just write the superblock header multiple times. So again, I'll say it slowly. There are just I think 6 copies. Well, I think it's 4. There are like 4 copies of a superblock header on disk. And when replica starts up, it reads all the 4 copies. And then across all the 4 copies, it picks the most recent, the most latest, because I think, yeah, or every superblock instance is stamped with sequence number. So if you like want to update your superblock, you write 4 copies, you have written like only 2 of them, and then you crash, and then you restart, and well, then you read 4 different copies. They have different sequence numbers, but well, the 2 with the higher sequence number is what you should pick. I probably won't be looking at how exactly we read the superblock today. I'm going to keep today's episode more hand-wavy. And we'll do a really deep dive there in a week. But yeah, that is sort of like the idea. All your data on disk is immutable. So once you've written a table to disk, it stays there. It never changes. The way to append new data to disk is that, well, you create a new table completely separate from what you have, and then you insert it as the topmost level in your LSM tree, such that the data in this table shadows old data. So instead of deleting the old data, we shadow it with the correct version. Now, obviously, the way we insert this table in memory is like pretty trivial. We just like go and insert in our like in-memory LSM manifest data structure, which is segmented array. Never mind. How do we insert this on disk? Well, we collect a bunch of insertions into a new manifest node block, and then when the manifest node is full, we take this node and write it to disk. And again, the old manifest stays intact. There is a linked list. Linked list is a persistent data structure, a data structure which you can cheaply update without rewriting the parts. So manifest node, manifest log node contains these like insert table, delete table operations. So when you like add a node at the top of it, it like naturally shadows all the previous tables. And then so you have like at one point you had like this pointer to here I need to start drawing things. I'm set to say this. Okay, xcalibro.com. Okay, that didn't work. Okay, so you have your manifest blocks. So this is manifest, and manifest nodes point to each other. And then there is like a superblock. Superblock, yeah, it's going to be a rhombus. So this is superblock. And okay, oh my dear. This is, I need to go back to reasonable size. Okay, so we have manifest log, manifest log node, and there is like a bunch of this. Like We are not even seeing the end of it yet here. And then there is like a super block. Super duper block. Okay. And it contains a DSR state, which contains checkpoint state, which contains pointer to the very first manifest node. So when we want to mutate the state of our last entry, what we're going to do is that we are going to create a new manifest node. And we are going to point from this manifest node to this manifest node. So we kind of like, again, manifest node stores insert table, remove table operations. So for example, if you want to add new data, we have here like insert table. And if we want to remove data, we have here like delete table. And this delete table kind of like shadows and overrides insert table over here. Okay, and then, although we have written this new manifest node to disk, it is not really visible because our super block is still pointing to this old data. And if we crash and restart, we'll actually sort of forget about this node and we'll start again from our like old state. So, to finalize this state transition, what we need is that we need to create a new super block. Okay, no. How do I do this? We need to create a new super block. And we need to point out that, hey, this new super block now points to the new manifest log node. And then we finally replace the super block. So this is the thing. This super block, again, it is actually written in 4 different copies. So the idea here is that if we are updating our super block, we want to make the update logically atomic. But to make it logically atomic, we overwrite each of the 4 copies. And that means that no matter when we are interrupted in this process, we can always get either the new super block or the old super block. And that's why we always restart in a consistent state. Okay, new question in Twitch. How does the infinite chain of manifest nodes get garbage collected? It can't go forever, right? Yes, that's an excellent question. And indeed, well, I think, I wouldn't say that something would necessarily break if you just never garbage collect manifest nodes. Well, that means that your startup time is going to get slower and slower, but I don't think that actually you'll have any physical limit why you can't make this infinite. But of course we want to keep the size of this chain of manifest log blocks limited because, well, we want to start up faster. And the idea here is to run compaction. So let's zoom in into these manifest blocks. So let's say that in this block we have operation add table address 64 to level 2. And in this block, we decided, hey, we actually no longer need this table. So we say remove from level 2. Now, what is interesting here is that these 2 operations, add table and remove table, they sort of can cancel them out. So if we keep the same blocks, but just remove these 2 entries, we'll get the same logical data, but using fewer physical bits of disk space. So how do we do it? And that's actually a compaction process. Okay, that's interesting. Let's keep this. Let's keep the episodes about like everything. So. Okay, I don't remember in details how this works, but essentially, let's say that okay, let's start our zoom inflation here. Let's say that this is your entire manifest log, so only 4 nodes. And then this last table has like insertions for like table X, Y, and Z are here. So what you can do is that you can read this latest block about tables X, Y, and Z and check which tables actually are there right now. So, but at this moment we have, say, tables X, Z, W, T, U. So we know when we started we have tables X, Y, Z, and when we ended we have tables X, Z, W, T, U. That means that somewhere between this block and this block, table Y got deleted. So what we can do is that we can take this block, just remove it from the manifest, and append it to the beginning. But this time we could actually go and cross out the table Y. So no table Y here, because there is, okay, let's color code this a little bit. Okay, I don't think I can color code individual letters, but okay, I think I can underline them. Okay, so we have X and we have Z, but we don't have Y, no Y here. So we essentially cut this node, took only the information that is still relevant and appended it on the top. And you see, this is actually something we covered last time. If you look at this super block, what is what checkpoint state? Look at this checkpoint state. We actually have 2 pointers to manifest blocks. We have the pointer to the first entry and the pointer to the last entry. So the full picture is going to be that, okay, originally, okay, let's inflate our zoom a little bit more. Okay, so let's actually, okay, so nothing, again, everything's immutable, nothing is deleted. So original picture was something like this. This is our like super block. Then, after we compacted the manifest, what we got is something like this, but this one is green, and then the new super block now points to this. No, I want this to be red. Now points to this and to this node. So you see here, like we kind of like prepared the node in front and we removed the node from the tail. And actually, I think we've seen this in the source code. And I remember it was like actually pretty hard to find out on. Okay, manifest log. Okay, yeah. So this is the code which reads manifest log from disk, and this is the callback when we read the block. So after we read the block, we go and process all the manifest entries there, and then we are going to read the previous block. And and here we check whether the block we've just written is the oldest block we should read. And if we are here, then we don't proceed further. Otherwise, we proceed. And the key thing here is that actually, like this maybe should probably be actually inserted here because it's important. So it might be the case that, hey, this block isn't actually physically the last block in the manifest, and that it points to a next block which was there, but well, which is like now logically removed. So that's why when we follow this linked list of manifest log blocks, we stop not when we reach the null, but actually we stop when we reach the end block as we know it. Okay. Okay, let's tie this everything together. How the data actually gets evolved in target. So imagine a replica. You start up. You read your data block. You start reading your data block by reading the super block. In particular, you read the 4 copies of a super block. Because you read redundant copies, this actually allows you to reconstruct with high degree of certainty what your actual latest super block was. After you read the super block, you can follow this trace of pointers to read the entire manifest log and to reconstruct the set of all the labels, all the levels, and all the tables. It's curious that label is not a combination of a level and table. Those are separate things, but well, linguistically it would have made sense. Okay, so you read the set of tables, you read the set of labels, you reconstruct the data in memory. Now, this data is frozen. It is like immutable. You cannot just go and mutate the set of tables, this set of labels. So when you are processing transactions, instead of modifying the old tables in place, you go and write new tables. So, for example, if you set like you had key x and it was pointing to 2, and now you want to make this kx point to 92, you create a new table which contains this x equals 92 entry, and you append it to your in-memory data structure representing the manifest level. And then you append it to an in-memory buffer which contains pending modifications to your manifest. And right now, like all modifications happen in memory. So if you crash at this point and you restart, you will actually restart without that extra modification. And you would have to apply changes from your write-ahead log. But well, because you do store all the transactions write-ahead log, you could actually like replay this change and get exactly the same state. So kind of like again, in the middle of this all, you have your original data model, which is on disk, which is still intact. Then you have some in-memory diff for the data model. And then you have some new things written in different places of the data file, which are not yet like persisted because they are not in the superblock yet. But then in the end, once you've accumulated enough of those changes, what you actually do, you go and write a new superblock. And this new superblock points to new data. And that way you kind of like durably persist changes. Okay, so I realized that I really need to start drawing things here. Okay, so yeah, probably I was hoping to do a little bit of a code dive today, but well, it's going to get to be 0 code dive and 100% of hand waving. So okay, so this is our data file. This is our okay, I need to de-inflate the zoom. Okay, data file. At the start of the data file, we have the super block, which is actually 4 copies. Super block x4. This super block points to the manifest log. So okay, I'm kind of like drawing rectangles is too hard. So this thing is manifest log. And like manifest log like ultimately points to tables. So we have like this. So this is like a rudimentary table, and this manifest log nodes ultimately point to those tables, and yeah, that's kind of like frozen state when, as a replica, you start. Well, okay, no, it's not the entire state. There is. Okay, let's draw it somewhere here. So kind of like green, like a relatively small but important thing. This is like right ahead log. Okay, so this is like frozen state at the start. Like you just restarted. This is okay. Before I proceed, another question from chat. The manifest log points to tables, but tables make up trees, and trees make up forest. Are forests not represented directly in this manifest? So far, we haven't talked about forest almost at all, because at this level of understanding, like forest isn't actually important. So, what is a tree? A tree is a sorted set of values. What is a forest? Forest is a set of trees. Kind of like this. Data block, index block, manifest log node, manifest level, manifest is like a vertical dimension. We look at a single tree and we look at the parts which compose this tree, like kind of like atoms and electrons and whatever. Forest is orthogonal dimension. Forest is what you just like have like a tree for storing accounts and then a tree for storing transfers. So like you don't need to represent the trees here, because essentially, kind of like one like stupid way to represent the forest is just like take this picture which represents a single tree and then just like duplicate it and say, okay, so this is like tree 1, and then next to it this is like tree 2, etc., etc. So that's just like programming abstraction kind of thing. What physically happens is that manifest log is actually shared across all the trees you have in your data file. So there is like kind of like physically the way tree is represented is by a type. So different tree is just a different compile time type in the Zik code base. And in general, like the data of different trees exists in completely separate dimensions and doesn't interact with each other. except for this manifest log thing. So a manifest log is type erased and stores entries for all of the trees at the same time, actually. So kind of like essentially each tree is isolated, each tree doesn't know about each other, but within the manifest log nodes, they're actually the same. They actually reuse the same nodes. So if you look, and that's actually a great question, because it will show, it won't show a like super neat aspect of Zig, because I will have to do an entire lecture about it, but well, at least they point out in the code where this happens. So if we go back to the manifest log and look at the manifest node and look at the table info that it stores, which is again, address of a table, level, and whether this table was inserted and removed. You see that there is like this tree ID. And tree ID is just a number. And this is what identifies tree in a forest. And then in the forest, we have tree for ID type, tree for ID function. And that is a function that, given the U16, the number of the tree returns a specific type of the tree. So this is kind of like, this is your compile time. The problem is that manifest log. Okay, I lost this. Where was this? Table info. Yeah, the problem here is that this tree ID is runtime known. And this function kind of like requires tree ID to be comp time. So imagine, okay, so you read the tree, like you read manifest log node, and it says, okay, this is some entry for like tree number like 92. And you're like, okay, so 92 is like the runtime number, but like how do I get like this type of the tree? Again, in a language like Java, you would have some like RTTI to just say, okay, so this is like some interface or whatever, like I don't care, like here is how we transfer between like runtime and types. But in Zig, you need to do something different. And the way you would like do this in Rust, you would actually say, okay, let's just switch on our tree ID. So kind of like again, fn pretend this is Rust. So we have ID, which is like U16. And you would do something like match ID. So if this is 1, then we do type A kind of thing. This is 2, we do type B, etc., etc. So in Zig, we actually do exactly the same, except that we use inline switch. So let's see how it is called. 3.4 ID. Well, it would be embarrassing if we aren't actually calling this function. Okay, yeah, this is it. So here we have, well, again, it's manifest log open, where we have a type erased table. We look at the true ID, which is a runtime value, and then we do an inline switch here. And here, this true ID is comp time. And here we get a tree of a specific type and then ask, hey, this particular tree, please open the table. This would not make any sense for you unless you are Brian. And even if you are Brian, it probably still doesn't make sense for you. But at least you now know the place in the code where you could look and see where this type erased true ID turns into actual compile time type of the tree. Okay, anyway, but this is not what I want to show here. I want to show like the evolution of data. So okay, what is this? This is data file. This is data file when a replica just starts up and opens. It is just static. Now, let's see what happens. Again, some zoom inflation here. Let's see what happens when the replica starts appending new data. Well, every new thing that arrives at the replica arrives in the write-ahead log. So this is like, it's actually, caption is probably, this is a batch of transfers. So replica goes and appends the batch to its write-ahead log. And then it appends these results from this batch to some in-memory hash map, essentially, in-memory state. So this is kind of like the state of the replica once it accepted small amount of new transactions. The state on disk is exactly the same, but then there is like some amount of in-memory state. So when replica answers any queries or does any kind of computation, it goes to the in-memory state first, and if it finds the answer in the memory state, it returns it. If it doesn't find the answer in the memory state, it goes to disk and reads answers from there. So again, if we crash at this point, so just boom, like big ugly crash. When replica restarts, it of course won't have this in-memory state. So in-memory state is like completely gone. But what it would have, okay, no, it wouldn't have this thing. Okay. It would still have this thing written in write-ahead log, because, well, we write data in a write-ahead log immediately. So when the replica restarts after the crash, it says, okay, so this is my local state, but also I have this batch in my write-ahead log. So before I start processing any new requests, I'd better to reconstruct my in-memory state. So again, if we crashed without applying anything to the disk, we can restore, due to determinism, our in-memory state and continue processing further transactions thanks to our write-ahead log. Now, what happens if you have more batches? Okay, move this to lock, I think. Okay. Okay, I know. I will just do this again. I really love doing things again. Okay, after recent Linux upgrade, for some reason it really poorly handles drag events. So sorry for these kind of stupid errors with mouse. Okay. Really, Wayland is a joke. I cannot even drag things quickly enough. So okay, well, that was my mistake. I cannot also copy things. Okay, so let's say we accepted a bunch of more batches, so that the in-memory state is kind of like big. Really cannot. Yeah. How can? Linux is the best operating system to not use on your desktop. Okay, so our in-memory state has grown large, and we want to start spilling some changes onto disk. So what we do is that we, let's say that we create a new tree, and we also create a new manifest node, and we say, hey, this manifest node now points to this new tree, and it also points to the old manifest node. So this green stuff here is the new data. And now, imagine that you crash in this situation. Yeah, if you restart, what happens is that, well, this green nodes, as green stuff on disk is kind of like still there, but it is not reachable from your superblock. So this green stuff is actually like invisible. So it is there, but it is like, can I just say that it is white? Yeah, so it is kind of like there, but kind of like also not really there because it is unreachable. It is invisible. And what happens here is that Replica still has these batches in the write-ahead log, so it starts replaying transactions again from this old checkpoint, and due to determinism, it actually ends up reconstructing exactly the same state. So again, we crashed, we restarted, and we reconstructed exactly the same state, including our modifications to the data file, which we redo again. But again, these modifications are not durable. So after getting even more batches and growing this new state even more, Replica decides that, hey, okay, so at this point, I accumulated too many things in my write-ahead log. And if I crash now, it would take me forever to replay all this data starting from my current checkpoint. So I need to switch to the new checkpoint. And well, I kind of like didn't formally introduce this checkpoint, I think, but that's a keyword here, like the checkpointing. So checkpointing is basically writing the new superblock. So Replica figures out that, hey, I actually need to do new things. And then it starts overriding superblock with new copies, which actually point to this data. And if Replica successfully have written, I think, at least 2 copies of the new superblock, then when it starts next time, it actually is going to use this new data because it is now visible, because it is pointed to by the superblock. And that is, folks, how you mutate persistent data structures on disk. So, okay, we are 7 minutes over time. I think that's it for today. Today turned out to be like super packed episode where we covered like everything from the checksums to checkpoints. Well, maybe not everything, but definitely everything between check and check. Don't worry if this doesn't make a ton of sense to you now. I think we'll spend at least like 3 episodes diving really deep into how this actually works and looking at the code and like tracing this overall evolution of data. But yes, the idea is this. The idea is that you store data on disk. You store data on disk in persistent data structures. The way you mutate persistent data structures is that instead of mutating in place, you write a new data structure alongside the old one, and then you atomically swap the root pointer to like where the data structure starts. And for us, the root pointer is like this, the first manifest log node. And to kind of like amortize the cost of swapping the root pointer node, you only swap root pointer once in a while, because it is actually not an error to not update the root pointer every time, because even if you didn't update the root pointer, you still have your write-ahead log. So if you crash and restart, you can start from all checkpoints and play forward all the changes before that. Okay, let's end it here. Just one small question. Okay, thank you, Brian, for answering one small question for me, and especially thank you because, yeah, pasting the link to the YouTube recordings of all these lectures is exactly what I needed to do, but I was not able to do this because, well, I am logged out of Twitch account at the moment, but thankfully we have many viewers who could share the link. Okay, so see you next week at 5 p.m. UTC here on Twitch. And if you manage to miss this lecture, or if you want to catch up with any of the previous episodes, of which there are quarter of 100 already, then please visit TagGabriel's YouTube channel, which contains Iron Beetle playlist, which contains all of the previous episodes. Thanks again for watching, and especially thank you for asking questions in Twitch. That's why it is live on Twitch, because I do want to answer any questions you have. Goodbye.